Afternoon to all of you and welcome back to the 14th lecture of STAR 2026. Today's first lecture is on submillimeter astronomy by Professor Baswati Mukherjee, TIFR, Mumbai. We welcome Professor Baswati to STAR 2026 session. This session will be moderated by Dr. Veena V.S., faculty member in the Department of Astronomy and Astrophysics, Tata Institute of Fundamental Research, in short, TIFR. May I welcome Dr. Veena to moderate the session by introducing the speaker and to conduct the session. Over to Dr. Veena.
Thank you. Good afternoon, everyone. A warm welcome to today's lecture. So we have today Professor Baswati Mukherjee from TIFR. She did her PhD under the Joint Astronomy Program of Indian Institute of Science, Bangalore, working at TIFR. Subsequently, she held a Humboldt Fellowship at the University of Cologne in Germany, followed by a Franker Fellowship at the University of Maryland in US. Since 2007, she is a faculty member at the Department of Astronomy and Astrophysics, TIFR, and is the chairperson of the department since 2019. Her research focuses on the physics and chemistry of the interstellar medium, the formation of massive stars, and their impact on the surrounding interstellar medium. She is also an expert in the infrared and submillimeter observations as well as instrumentation, and she is the science PI of the proposed first Indian submillimeter telescope. She is also leading a team developing the next generation submillimeter instruments. So without further delay, I welcome Professor Mukherjee and invite her to begin the lecture.
Thank you, Dr. Veena. I thank ISRO for organizing this program. I hope everybody can see my slide. So today's lecture, as you heard, it will be on submillimeter astronomy. And you will see quite a few nice images. And as you see some of them in the cover slide, as we go along, we learn what these things are. So first, let me tell you what exactly are the topics that I'm going to talk about. As you probably heard or read about the short brief on what this lecture is going to be, that the submillimeter wavelengths help us to trace the cold and dark universe. So the first thing that we will learn is that what do we know about the cold matter between the stars, and then why observations at submillimeter wavelengths are needed to study them. Then we'll also discuss a bit on with where on the Earth can we observe in the submillimeter wavelengths. That question obviously tells you that it's not possible to do it everywhere. And finally, I will give you a glimpse of some of the excitements in science that scientists that we have learned or we are enjoying because of the studies in submillimeter. What you see here is on the left panel an image of the night sky. Many of you may recognize the constellation with the bright stars, that is Orion. And that is the night sky that you probably are very used to seeing. And this is what the visible wavelengths show us. Like when we observe, we are observing the visible wavelengths, and this is what we see. We have these stars and interspersed with huge dark space. However, if we observe the same sky using a near infrared or an infrared telescope, which means that we are actually observing at slightly longer wavelengths, then we realize that the space between the stars is not empty. So it is still the same Orion nebula. Orion constellation. You can see the bright stars. This is the belt of the Orion, and this is the sword. And actually, the sword has a very bright source, which is even more bright in the infrared, and that's the Orion Nebula. It's a very active, or one of the nearest massive star-forming regions. So you see that there is also a lot of matter, which sort of is. Which basically is matter which is illuminated and pretty hot in that sense, that is between the stars. Now, yet another picture which you may be very familiar with is the Horsehead Nebula. The Horsehead Nebula is also something which is near to us, but on the left-hand side, what you are seeing is a picture. It is called a nebula, but what you see is a dark cloud, and it is basically a silhouette, means something very dense and dark matter which is illuminated from behind. It's so dense and dark that it doesn't let the light from behind pass through it. This is once again a visible image. And if we zoom in on the head of the horse head, or on the horse's head, we see this and look at it with using an infrared camera. Infrared, by the way, is something which is sensitive to heat. Anything which is warm emits in the infrared. We will go into the what exactly is the range of wavelengths, etc., a little later. So this is the infrared. So this is the infrared picture, and we see that actually there is a lot of material which are also emitting, but emitting at a different wavelength than in the visible. So what is it? What are the things in between? So based on these and many other observations, what we realize is that the interstellar space, that is the space between the stars, is filled with dilute dust and dust and gas. So what is dilute? By dilute, I mean that the density of, or the particle density is very low. So to give you an example, when one says talks about dense interstellar gas, then one says that it has about 1 million particles per centimeter cube, which if you calculate is really, really very dilute compared to the densities that we see all around us. And now in what form that gas can be? It can be an atomic or molecular form. It can be diffuse, distributed and diffuse, or it can be clumped into dense or diffuse clouds. Now, these dense molecular clouds are of particular interest to the scientists because these are the places where new stars are being born. And stars are an important component of the galaxies because because they undergo nucleosynthesis at the center. They synthesize newer elements, and also they, as they age, they actually undergo various stages of evolution. You may have heard about those. And so then beyond, and after some time, when the star is near the end of its lifetime, it actually dissipates, and it actually ends its life in a sort of a violent, suffers a violent death. And so then it disperses everything into the interstellar space once again. So actually the stars help in enriching the chemical content of the galaxy. So they play an important role in the evolution of the galaxy as a whole. So it's very important to learn how the stars are forming in these clouds. And that's one of the, I would say, one of the prime motivations for studies in the submillimeter. Now, coming to the question of so this is here again, what you see is the same matter between the stars. On the left, you see the picture of an image of the spiral galaxy M51, also known as the Whirlpool galaxy, in the visible wavelengths, where you see the stars as bright spots, but you also see dark lens. These are like in the form of spiral arms. And these dark lens actually correspond to very cold and dense regions of the interstellar space. And when we observe the same galaxy in the infrared wavelengths, longer wavelengths, we see that actually the dark spaces are no longer dark, they are emitting and they're bright. Actually, those are the places where also new stars are being born. So this makes us so this actually looking at the such regions at longer wavelength helps us to understand the stars while they're being born, and or any other structure while it is being formed. Now, so to understand fully, like I will just tell you that what all is there in the region between the stars. As I said, there is gas. And if you know that, so most of the gas is hydrogen. So here on the right, what you see, what we sort of call the astronomer's periodic table, where hydrogen, because it's mostly hydrogen. If you see the number of particles, like relative to hydrogen, how many of the other elements are there. So the next most abundant is helium. And then all the other elements that we are very familiar with, like carbon, nitrogen, oxygen, they are actually about more than they're like 3 times 10 to the minus 4 in relative to the by number relative to hydrogen. So they are actually very few in number. So, but even then they play an important role, as we know from our studies. So these the gas as could be in the gas, the elements could be in ionic form, they could be atoms, and even there are molecules. And these things are all moving around with velocities that are reflective of the temperature. So mostly this is what the interstellar gas is. But the region between the stars also contains another type of particles which we call interstellar dust. These are basically small solid particles which are less than a micron in size, mostly around 0.1 micron, and they're mixed with gas. They actually are very by mass they form a very small fraction of the interstellar matter, but they are very important in they play an important role because they absorb and scatter starlight which is passing through that. Here on the left hand side, what you see is that there is a interstellar cloud and there is dust, and the stellar radiation when coming, depending on its wavelength, gets preferentially either more scattered or absorbed. So the blue light is more scattered, whereas the red light can pass better through. So what effectively happens is that it either absorbs all the light from the star if there is an interstellar cloud here, or it actually removes the photons from the line of sight, which is equivalent to also that the starlight never reaches the observer. So it actually makes the that's why we do not see anything in the visible. We do not see any stellar emission between the stars, because there are lots of stars behind the interstellar matter, but we do not see them. And these particles are, as I say, they're something like 0.1 micron, and they have some, they are made of graphites and silicates. And since they're very cold, they have typically temperatures between 10 to 30 Kelvin. They often have, they're coated with ice. This ice can be of water ice, or it can be methanol or any other molecule. It's like having a cold surface, and you have, when there are a lot of gas molecules going around, if there is a cold surface, then the molecules stick to the gas surface and then they freeze. So this is the structure of the dust grains, and they play an important role in making most of the starlight invisible to us in regions which are very cold and hence dark. There are two other components which I will not go into details, but for the sake of completeness, I will mention. There are also a large number of very high energy particles, mostly ions and electrons, which have kinetic energy much greater than thermal energy, and they move with like relativistic. They are also highly relativistic and have energies of the order of 10 to the 21 electron volts. Also, there is we have detected, the scientists have detected interstellar magnetic field of the between 5 to 20 microgauss. We do not understand what those are, but we do see their impact, and we can observationally we can verify what are their strengths. And one important thing to understand is that when there is a magnetic field, if there are charged particles like say the electrons or even ionized gas, then the charged particles actually follow they can move only along the magnetic field lines. And so these magnetic field lines can then be they can be also dynamically important in the sense that they regulate how the gas particles can move in a particular region. Now let us understand obviously all these things are happening way far away from us, and we can only detect these things if there is an emission by observing the emission that's coming from. So now what kind of emission does come from the interstellar medium? Let's look at the emission that we know as continuum, which means that the emission which spreads over a large range of wavelengths. And now what kind of temperatures would the interstellar matter have? It has temperatures between, say, it can be as low as 5 Kelvin and typically between 10 to 13 Kelvin, depending on how far they are from the stars. If they're very close to the stars, they can be the interstellar matter can be as hot as 2000 Kelvin. But then in most places, because the space between the stars is vast, the temperature of the interstellar matter typically is between 10 to 13 Kelvin. Now, if we have an object which has a temperature of between 10 to 13 Kelvin, and then the emission coming out of it follows a law, Planck's law. Most of you would have heard of it, and this is the functional form of it. And as you see that this actually depends, the emission at a particular frequency depends only on the temperature of the object. And many of you may be, so this is the functional form. Like if I make a plot, so on the right you see plots of the Planck function as a Planck function for different temperatures. So if the temperature is like our sun, which is around 6000 Kelvin, then this is the curve that we will get. The x-axis is frequency and the y-axis is the total emission that we have. So spectral radiance in some units, which is written there. So the total emission, the emission at every frequency that we get, if we make a plot. So this is what the emission from the sun would look like, and this is the range of frequency, that is the visible length. So if you notice the top x-axis, the wavelengths are given in millimeters, and here what you see is that these are in the hundreds of nanometers, like 400 to 700 nanometers. So the emission from a star like the sun it actually shows a peak around in the visible. Whereas if you look at our Earth, it has a temperature of around 300 Kelvin or maybe 280, 290 Kelvin. Then it is peaking at temperatures which are like peaking at wavelengths which are much longer. And so this is more like 0.02 or 0.03 millimeters. But if you consider objects which are like 10 or 30 Kelvin, which is similar to the temperature as the interstellar medium, then you see that they tend to emit the emission peaks at around around 0.1 to 0.3 0.3 to 0.1 to 0.3 millimeters. So this also can be derived if you consider the Wien's displacement law, which tells you that the wavelength at which a black body radiates the most is related to its temperature in this way, where B is a constant. So which means that the thermal emission from the interstellar matter, which is primarily dust in this case, which has temperatures between, let's say between 5 to 100 Kelvin, will peak around 0.1 to 1 millimeter. So this is the sub-millimeter, or even you can say that you can stretch it to 3 millimeters, so sub-millimeter or millimeter wavelengths. And observations tell us that actually about 30 to 50% of the total luminosity of the universe, of the matter that we see, lies in this waveband, because most of the space is very cold. So this is about the continuum emission, which is spread over a range of wavelengths. But the interstellar medium, as I said, also has gas. So this gas, and I said that the gas could be atomic, ionic, but it also molecular. So at temperature of about 5 to 30 Kelvin, if the density is high enough, if there is enough number of hydrogen atoms, then they start to form molecules, and so most of this gas at between 5 to 30 Kelvin is molecular, but molecular hydrogen itself does not have any rotational transitions or spectral lines at these wavelengths, which can be excited at these wavelengths at these temperatures. So instead of that, there are other rotational lines of molecules like carbon monoxide, which is the next most abundant molecule after molecular hydrogen, water, and also hydrogen cyanide. They all have transitions which lie once again between 0.3 to 3 millimeters, which I would call to be the sub-millimeter or millimeter regime. So, and just to tell you that although, as I said, that the interstellar gas is extremely dilute, there are more than 350 molecules which are detected in the interstellar medium. So, and here you see a picture of the figure which shows all types of molecules which have been seen. You see that pretty complex molecules. These are all organic molecules, and they have been detected in the interstellar medium. So what we see is that it's not only so the what we see is that it's not only the dust emission from the matter between the stars, but also the molecules. They primarily emit in the sub-millimeter wavelengths, which is between say zero point 0.1 to 1 millimeter. And if we just restrict ourselves to if we restrict ourselves to only a sub-millimeter, but you can consider 1 to 3 millimeter, also the millimeter, because also as the range for which all of the what I said applies. So the cold matter between the stars is best stressed in the sub-millimeter wavelength. So this justifies why we are interested in observing the universe in the sub-millimeter wavelengths. Now, the next question is that, okay, so can we observe the sub, if I am able to build a telescope and put it, say I'm currently in Bombay, would I be able to see sub-millimeter radiation? Probably not. That's because our atmosphere actually prevents the radiation. Well, it prevents a lot of radiation from entering the earth, which is actually good because it protects us. But particularly in this sub-millimeter wavelengths, the atmosphere is selectively transparent. In this plot, what you are seeing is on the x-axis I have both frequency as well as wavelength. So here it goes from 0.15 millimeter to about 3 millimeter. So this is longer wavelength. So as you can see that up to about 300 micron or 0.3 millimeter, the atmosphere is selectively transparent. So the y-axis shows if it is whether the atmosphere is transparent, and this is actually, as you will see, that it is at one of the best sites where you can do sub-millimeter observations, not on this at the sea level. So the transmission is about 100% basically at longer wavelengths. But if we are in the sub-millimeter regime, which is between, say, this is that 0.3 to 3 millimeter, we see that the Earth's atmosphere is selectively transparent, and the transparency is also like goes only up to 60%. And so these are called windows. So there are some, sorry, so the windows are open, but rest of it is like blocked extensively. So we see that there are some selected windows where we can observe the radiation from the Earth. And what is this? What is there in the atmosphere which absorbs it, which matters for this sub-millimeter regime? Basically, the atmosphere also has molecules like water, oxygen, and ozone. Water is not just water itself, but also its other isotopes. And so if the molecules are there in the atmosphere, so the radiation coming from the astronomical sources or from outside of the atmosphere get absorbed by these molecules, and so they do not reach us. So that is what causes the opacity of the atmosphere to the sub-millimeter radiation. So, and particularly the water vapor lines are the main lines which limit which dictate where we can observe, where are the spectral windows through which sub-millimeter observations can be done. And in particular, these water vapor lines, what they do is they are like well spread. So they not only absorb the astronomical signal, but they themselves emit thermally. So it is like if you have so they themselves are emitters of and strong emitters of radiation in the sub-millimeter wavelength. So they can actually overpower the radiation, that the faint radiation which is coming from very distant objects like the astronomical sources. So which means that we need to go to so there are two options. One thing is that, okay, we can send the sub-millimeter telescope in the space where we do not care about the atmosphere, or it can be located in particular locations on the Earth where the water vapor lines do not affect or do not there is less water vapor in the atmosphere, so that they do not absorb the incoming radiation from the astronomical sources. So there has been only one like a big scale sub-millimeter space-borne sub-millimeter telescope. It's a satellite borne. This is called the Herschel Space Observatory, and it was launched in 2009. So it could make observations between 0.055 to 0.672 millimeters And it had a mission life. It operated for about 4 years between 2009 and 2013. I have provided this to tell you. So it was a 3.5-meter telescope, and actually it was the largest telescope till JWST, or the James Webb Space Telescope, was launched. That which operated in the infrared and submillimeter. And then, so it also had onboard instruments which could do spectroscopy as well as take nice images of the interstellar space in these wavelengths, which meant that they were actually looking at uh, detecting both dust and gas, and they were trying to, these observations helped us to understand what are the conditions of matter between the stars, because that is important to understand the initial conditions of formation of stars. And that's one of the prime motives of motivations to make observations in the submillimeter wavelengths. Now, as I said, so now that was the spaceborne thing. But suppose we still want to build observatories on the Earth. What kind of a place would suit to build this submillimeter observatories? First of, since water vapor is the primary cause of the atmospheric opacity, the best sites must have exceptionally dry air. And typically, water has an exponential scale height of 1 to 2 kilometers. And so, which means that one needs to go to high altitudes, particularly in the subtropical desert regions. And also, so most of as you will see that most of these high altitude sites, which are good for submillimeter observations, are located in desert regions, subtropical desert regions. Also, they at the low temperatures of the Antarctic plateau, the saturated air has very small water content. So that also is a very good site for submillimeter observations. So here I have so on the world map, you see what are the primary sites where currently submillimeter observatories are have been constructed. And also, so you see this is in Hawaii, which is an island. On top of the mountain Mauna Kea, there are multiple submillimeter observatories or telescopes. And then the latest is the Chandantur plateau in Atacama. It is basically the highest and driest plateau, and it hosts many multiple submillimeter telescopes, including the Atacama Large Millimeter Array, millimeter and submillimeter array. There is an Antarctic plateau where also there is South Pole telescope. This is somewhere here. And so there are two other sites which are actually very suitable for submillimeter observations, but the submillimeter telescopes are not there, but the sites themselves are promising. One is in India. It is located in the Himalayas. It is actually very close to the Indian Astronomical Observatory, where the Himalayan Chandra telescope, which is a 2-meter optical telescope, which is there. And this is highly suited. The climate and the weather pattern there is highly suited for submillimeter observations, and ISRO has proposed to build a submillimeter telescope. Since this is still in a proposal phase, I will not talk much about it, but some of us are involved with it. Of course, on the Chinese side, which has equivalent weather conditions, the Tibetan plateau is actually there already exists one submillimeter telescope, but then there are more which are coming up there. Okay, so now where else? So what are the submillimeter telescopes? Like maybe this is for the first time that you are hearing the submillimeter telescope, but I think many of you may have seen the picture to the left, which is the first image of the black hole associated with M87, a galaxy. And although, so this you may recall was actually observed with something called the Event Horizon Telescope, and which is a global network of, at that time it said radio telescopes, but these observations were actually done at 1.3 millimeter and 0.87 millimeter. So which means that these are actually submillimeter observatories, and you can see all of the participating telescope which are there. So they are like ALMA is of course there. So they are broadly located in these parts of the world, and of course, yeah. So and they work together in a basically in an using interferometric techniques to produce this fantastic high resolution image of the black hole, first image of the black hole. And so, as I said, India also has a good site in the which is near Hanle, because that is extremely dry with very low rainfall. And systematic studies have been done which shows that this can be a potentially very good site for submillimeter telescope. This is to tell you, but we still do not have a telescope on our Indian soil, but the efforts are going on. So now let's take a look at, as I promised, that we'll take a look at what are the exciting science that people do with the submillimeter telescopes. The first thing is so you see here, you see the picture, the background in both panels, they actually show very dark clouds. So these clouds are so dense that they are dark, that they emit nothing in the infrared. Infrared is like slightly longer wavelengths, slightly longer than the visual. But if one observes them in the dust continuum at 875 micron, basically, which is like a little less than 1 millimeter, then one sees emission, because this is very cold, dark cloud. And if one also observes it using molecular lines like carbon monoxide, 13 carbon monoxide, an isotope of carbon monoxide, then also we see a lot of emission. So this actually means that the dark thing that we see in the infrared, which is called the infrared dark cloud, which is IRDC, that contains a lot of molecular material, which eventually will give and actually gives rise to newly formed stars. So such studies people do to understand how do this. So in the first stage, we also try to understand how do these dark clouds themselves form, and then how do the stars form in them. And such observations also help us to constrain the temperature and density of these clouds, the motion of gas inside the clouds. Then you know that, okay, how the velocity is, okay, what is moving towards what, whether matter is accreting or outflowing. And also it helps us to understand abundance of various molecules. So I showed you a graph, figure with spectral lines due to multiple molecules. So identifying the molecules, that is actually of interest, because we are still trying to find out what is the largest molecule that can be formed just in the interstellar medium without any intervention. And whether we can go, we do find molecules which are as large as the prebiotic molecules, because that addresses the question of origin of life and how did it start, where was it first formed. So this is one of the areas where the submillimeter observations make a huge contribution, and there are many other results that we can talk about, but for this in the interest of time, I'll just move on. So this is just to tell you that what we understand about star formation, that, okay, there is a cloud and then that forms a small core which continues to collapse, but because there is a rotation involved, a disk is formed, and that disk eventually forms what is called a protoplanetary disk, and in the sense that the planets are formed in there. And that brings me to the next topic. And before that, I will tell you the result I will show is an observation made using the Atacama Large Millimeter Array ALMA, which is located in Chile, and it consists of so many telescopes. It operates between 0.3 to 3 millimeters, and because it combines or it synthesizes a very large telescope using multiple telescopes, it can actually achieve very high resolutions between 4.4 milliarc seconds to about 0.5 milliarc seconds at say around 950 gigahertz. So, and this telescope is suitable to observe continuum emission from coal dust and line emission from molecules. Now, so why I said this, I talked about the protoplanetary disk. I said that ALMA has a very high resolution. So what ALMA enables us is to actually image disks around protoplanetary disks around stars. And what does that help us in understanding? It helps us to understand, okay, how planets might be forming. In one theory of planet formation, when this basically small particles on the disk on this protoplanetary disk, basically they coagulate and become larger and larger, and at some point it becomes large enough so that they form giant planets. And when they are forming that, so the small particles we start with are maybe dust grains themselves or slightly larger things, then eventually they form kilometer size objects which are called planetesimals. And then those planetesimals, they continue moving around the protoplanetary disk and collect material and become bigger and bigger and make a planet. But what you see in this this is a schematic, that once that planet has formed, it has actually cleared out some region within the protoplanetary disk. So one can no longer, there are gaps which are created within the protoplanetary disks, which are generally very cold objects. Like they are not as cold as the interstellar medium itself, but then they are more like about they go from 30 to maybe 100 Kelvin, but they're cold objects. So once again, thermally they will be emitting in the submillimeter regimes. So ALMA, the Atacama Large Millimeter Array, actually observed for the first time a fantastic image of such a protoplanetary disk in the H.L. Tauri star. And what you see here is that this is a disk, and here you see that it consists of, so this H.L. Tauri is a young star that is surrounded by a protoplanetary disk. It has a mass of about 10% of the mass of our sun, and it has a size of about 200 astronomical units, which is astronomical unit is the distance between the sun and our Earth. And so it is like a typical size of a planetary system. And these high resolution observations show concentric bright rings separated by gaps, which indicate the formation of planets. So this is a direct evidence of what the theory proposed, that okay, when the planets are formed, they will give rise to gaps. And but further studies have shown that these disks appear to be more evolved, and they indicate that the planets may be actually forming faster than what the theory had predicted earlier. Okay, so then let's move to the last exciting science that can be done in the submillimeter. Well, I've just chosen three, like last example, I should say. So there are galaxies. So when a lot of stars are forming in galaxies, they obviously produce a lot of radiation. But then when the stars are forming, actually they are forming from the material between the stars, the interstellar medium. So which means that typically many of those galaxies are also have a lot of dust. So what happens is that the stellar radiation is absorbed, but what happens that since the dust warms up, then the emission from the galaxy, it actually shows up that it basically that it is re-emitted around 100 micron or 0.1 millimeter. So this is what is called the spectral energy distribution of the galaxy, NGC 7714. You see two humps. The first one is due to the continuum, the radiation due to the stars, and the second stars are somewhat still processed by the dust. But the second hump which arises is due to the starlight which has been absorbed by the dust and then re-emitted. So this is what it looks like in a local universe. Like if some galaxy is nearby and it is forming stars regularly, then this is what you will see. But suppose such a galaxy is now very far away from us. So what that would give us is that, because when the galaxies which are very far away from us and they were also moving away from us, so this hump which shows up at about 0.1 millimeter actually moves to longer wavelengths, because it is redshifted, and then it forms, then it is at about 1 millimeter. So stay from 0.1 millimeter to it moves to 1 millimeter and beyond. So here what we are looking at is the emission from a galaxy at a redshift of 2.3, and these points that you see are the measurements that flux emitted by the galaxy, and so the red dots, and on that are plotted the spectral energy distribution of two of the nearby galaxies, which are like also called starburst galaxies, so which are forming a lot of stars at the same time. So which means that there are if the galaxies are basically located very far away at high redshift, like basically moving at higher redshift correspond relative to us, then the emission which for the local galaxies is in the infrared regime, will move to the submillimeter regime. So which means that if we want to detect very far away and dusty galaxies which are forming a lot of stars, submillimeter is the way to go. And in fact, this is what happened. In 2002, when a very powerful submillimeter camera was installed on the James Clerk Maxwell telescope, which is in Hawaii, a whole population of very luminous, high redshift, dusty star-forming galaxies was identified for the first time. So this is a galaxy which is like this. So in this view graph, what you are seeing are the optical galaxies, and the contours that you are seeing, they correspond to the galaxies, the submillimeter emission. So what you see is that we do not see anything corresponding to that in the optical or even in the infrared. So these galaxies which are very far away and they're at very high redshifts, they are very deeply embedded in their dust. So they do not emit anything in the shorter wavelengths. However, they are most actively star-forming galaxies in the early universe, and they actually release a significant fraction of the energy generated by all galaxies over the history of the universe. So it is only through observations in the submillimeter that we were able to detect this population, and we are now follow-up observations of these have tell us about the galaxy formation history of our universe. So I've tried to sort of select three of the I would say the most interesting results. Of course, the imaging of the black hole in the submillimeter is also as interesting. So now to summarize all that I have talked about is that, okay, so now let me just tell you about the images that I showed in the cover plot. This is a dark filament, and it is actually, this is a submillimeter image of an optically dark filament, which you see is forming stars. This is what I showed you is the protoplanetary disk, and this is obviously the first image of a black hole. All of these were, it was possible to observe only because we observed in the submillimeter. And here I put up the summary of what all I discussed in this lecture. Thank you.
Thank you, Professor Mukherjee, for this great talk. So now the floor is open for questions. Due to the time constraints, where I will restrict to some few selected questions. So the first question is, can submillimeter observations help in detecting prebiotic molecules and early signs of life?
Yes, the answer is yes, because as I said that the molecules, when they're large enough, like because the temperatures are low enough, so mainly what we detect are the rotational lines, and the rotational transitions typically form in the submillimeter and millimeter regime. So if we are to detect, we need very high resolution and high sensitivity. It will be possible to detect it using only in the submillimeter regime.
Yes. So the next question is, what type of detectors are used for infrared observations?
Okay, so I spoke here about the submillimeter. So let me tell about the submillimeter detectors. When one is measuring all the heat content of the, like in the continuum measurement, when we are trying to see capture all the photons that are coming within the submillimeter zone, then the most sensitive detectors use the principle of bolometers, which means that it's just measuring the total heat content of the object. And these bolometers can also be used to so these are essentially photoconductors. And when one is making spectroscopic observations, then one uses a principle called heterodyne principle, which is actually something we use in the radio, which is similar to frequency modulation of electrical signals, and that gives very high resolution. So the spectral resolution of more than 10 million. And so these are the two basic types of detectors which are used for the for submillimeter observations.
Okay. So one more question. Can we constrain the early galaxy formation models, for example, different dark matter halo models using the submillimeter? And secondly, can this be also used to determine the age of stars?
First of all, age of stars, not so much, may not be, but the galaxy formation and the early universe models are definitely constrained by submillimeter observatories. There is a new submillimeter telescope which is coming. It's called the Fred Young submillimeter telescope, which is coming up. It is actually dedicated towards detecting signals from very early galaxies. Both the spectral lines of redshifted spectral lines of singly ionized carbon, as well as very like imaging this and imaging of the galaxies in the continuum. And so determination of the age of the stars in those galaxies, well, I do not think so, but obviously the redshifts of those galaxies can be determined, but because we will we can have we will be also be observing spectral lines from those galaxies.
Okay, thanks again, Professor Mukherjee, for your nice talk.
Thank you so much.
Thank you, Professor Baswati, for providing an informative talk on submillimeter astronomy, and also our thanks to Dr. Veena for well moderating this session. Thank you both once again.
Thank you.
You may unshare, madam.
Yeah, sure. Okay, bye.
Somak Roychowdhury. Professor Somak is very familiar to the participants of this edition, as he provided a lecture on electromagnetic spectrum as the fourth lecture in this series. But for the sake of new participants, I would like to introduce the speaker. Professor Somak Roychowdhury is the Vice Chancellor of Ashoka University. He has undergraduate degrees from Presidency College, University of Calcutta, and University of Oxford. After his PhD from the University of Cambridge, he worked at Harvard Smithsonian Center for Astrophysics, where he also was part of the team that built the Chandra X-ray Observatory for NASA. After teaching for over a decade at the University of Birmingham, UK, he returned to India as Dean of Sciences at Presidency University, Kolkata, and went on to become the director of the Inter-University Center for Astronomy and Astrophysics, Pune. Dr. Roychowdhury is a fellow of the National Academy of Sciences. His research involves a wide range of topics in cosmology and astrophysics from the ground and from space. Welcome, Professor Somak, for your second lecture.
Thank you very much, and thank you for giving me the opportunity here. I'm very happy to be here. Shall I share my slides, because I have not tested it? Shall I just quickly?
Please.
Thank you. I'm hoping this will work. Last time there was a problem. Have to quit and reopen this. disturbances in the electromagnetic field, electric field or magnetic field in the things that we are studying. They can be stars, galaxies, quasars, black hole environments, etc. Now that we talked about how in that lecture, how the electromagnetic spectrum is much bigger than the light that we see with our eyes, and it goes all the way from radio microwave to high energy phenomena like X-rays and gamma rays, and these actually give you different parts of the picture of the whole physics of the actual object. And so this is how we learn, and not only looking at things that are maybe a few thousand degrees hot, but we learn about things that are a few hundred degrees hot in the same object, or a few million degrees hot in the same object, like galaxies or stars. But we also learn about the physical processes that are not thermal, and they generate parts of different kinds of radiation. Right. Now, in the last 2 or 3 decades, we have developed other kinds of sensors for messengers. We call them messengers, that brings information from the object to us, which are more than the electromagnetic waves. We see that even in the electromagnetic waves, I showed this in my last slide, that between X-rays and radio, or through visual and infrared and ultraviolet, we get different parts of our electromagnetic spectrum gives you different information about the galaxy. The UV talks about the hot stars, the far infrared talks about dust, the radio, as you saw also, the radio submillimeter that you saw in the previous talk, talks about the cold gas and certain phenomena, physical phenomena that produce radio waves. Now, if you increase your, I think some of the things have a little distorted now, but I will read out to you. The electromagnetic waves are photons, and they produce electromagnetic waves. But now you have other things that we can also find, which are not electromagnetic waves. If you look at below electromagnetic waves, we are talking about neutrinos. Neutrinos are particles that are very light, and they are also produced in cosmic processes that come to us in nuclear reactions that come to us from the sun and from all over the universe. And we'll look at a few examples. Here, the things that you cannot read, the top one is gravitational waves, which is what we are going to talk about today quite a bit. And this is something that in the last 10 years or so, we have been detecting quite a lot. And I'll talk a lot about gravitational waves today. You've had lectures on gravitational waves before, but I'll talk about how one can follow up gravitational waves. And the one that you can't read below gravitational waves, the fourth box, is called cosmic rays. And we'll talk about cosmic rays. Cosmic rays are particles other than neutrinos, high energy, massive particles that are coming to us. And you can see the energy range of these messengers going beyond the electromagnetic spectrum that I talked about now is much more. You can go up to much higher energies. The rate of the optical UV, etc., are around milli electron volts, and they go up to about electron volts to kilo electron volts in X-rays. And radio is micro electron volts if you look at the energies of these things. And we talked about how gamma rays in the electromagnetic waves can go up to GeV last time. But now, if you're looking at cosmic rays, which are very ultra high energy, and neutrinos, they can actually go up to 10 to the power 21 eV. And we are starting to look at really high energy phenomena. There is no way just through normal telescopes we can actually observe them. And side by side, parallel to all of these, are gravitational waves. Now, gravitational waves are generated not by electromagnetic processes, but by gravitational processes. And this is a different force altogether from electromagnetic waves. So this probes a very different physics from electromagnetic waves. There can be objects that have no electromagnetic waves at all, but because they are massive, they generate gravitational fields, and the changes in the gravitational fields will give you gravitational waves. So gravitational waves can come to us from objects which you don't see otherwise completely. And currently, the kind of energies that we are probing in gravitational waves is of the same order as the ones that we see in electromagnetic waves up to X-rays and things like that. But of course, gravitational waves can be of any frequency possible. Gravitational waves come to us because you see the space-time itself is curved due to mass, and that is what Einstein told us in his general theory of relativity. He also told us in 2016, a paper just followed his general theory of relativity, that if mass distorts space-time, and that is how we think of gravity in Einstein's gravity, then as masses move in this space-time, they will cause a ripple in the space itself. And as a result, there will be vibrations in space. And if you have very massive objects which collide with each other or even merge with each other, then they will cause ripples that can be detected. Now, Einstein himself, 100 years ago, in the paper he wrote in 2016, said that the ripples in space-time will have such small amplitude that you will not be able to detect it ever. But of course, in 2015, gravitational waves were actually detected from pairs of colliding black holes, as you will see. And they were detected for the first time. And now we have detected more than 300 such sources in the last 10 years. These give you information about the gravitational properties of objects. The gravitational waves propagate at the speed of light. They propagate just like waves, electromagnetic waves. They take energy from one part of the universe and take it to some other parts of the universe. They have polarization like electromagnetic waves. And what happens is that, as you see on the right, it causes oscillation of space-time. And so if, for example, there are things that are placed in a circle on space-time, they oscillate in two different modes perpendicular to each other. And that is how we detect them. The first gravitational waves were detected in 2015 by the LIGO observatories in the US. And they were detected using a Michelson interferometer like observatory, in which there are two perpendicular tunnels in which two laser beams travel and bounce on mirrors and come back. And they interfere, and they are in perfect balance unless a gravitational wave comes through. And as you will see soon, that causes a disbalance between the two. The first gravitational wave was detected in September 2015 by these two observatories, Hanford and Livingston, and that prompted the whole community to think of a third LIGO observatory. And this is, as you know, will be built in India, in the state of Maharashtra, near Hingoli, near Nanded, in central Maharashtra. So these three LIGO, and that is starting to build now. It will actually be operational in 5-6 years. But in the meantime, there have been other gravitational wave detectors that have been built in Virgo in Italy. GEO was already there in Germany, and one in Japan called Kagra. And these are now being built to detect gravitational waves. And they are very, very precise observatories that can measure displacements, which are of the order of 10 to the power minus 21 in strain. And so these are what they look like. LIGO Hanford and LIGO Livingston are two of these 4-kilometer long perpendicular tunnels with lasers going back and forth. LIGO India will be identical to that. This is an architect's view of what LIGO India will look like. Virgo is a 3-kilometer set of tunnels, and Kagra is also 3-kilometer set of tunnels, but Kagra is underground, and it is super cooled to cryogenic temperatures in Japan. All of them are working together now. Of course, LIGO India has not been built. And the way it does is that it takes a source that a laser source that is split into two parts. It goes to two mirrors. They come and combine. And what happens is that as a gravitational wave, you saw that it makes the space oscillate differently in two different perpendicular directions. And so it will make the two beams, as you saw, the half beams that are split from the same laser source, which are coherent. And as a result, in the detector at the bottom, you would find that you will get a signal of the two beams which were normally at balance. In here, it is at balance, but here you will find they move with respect to each other, and that interference will detect them. And that is exactly what has happened since 2015. And the first event that was detected was the merger of two black holes, which the whole, as you can see, this was the signal that came from the first merger, 1509-14. The whole thing lasted about 0.2 seconds, 1/5 of a second, in which one found the frequency of these gravitational waves go up in the characteristic fashion, and was modeled as a merger of two black holes. So this is all well known now. This led to a Nobel Prize. But can we find, so how do we know how to follow up things that we detect with gravitational waves? The multi-messenger bit means that now this is gravitational waves. Can we actually detect the same sources in other wavelengths, in other parts of the messengers, maybe in electromagnetic waves? And then we would find out exactly where this is coming from. So this first happened 2 years after that. As you can see, the name of the gravitational wave gives you the date of the discovery, 2017, August 17th. There was first a merger of two neutron stars that was detected, not two black holes, but two neutron stars. It was first detected by the two LIGOs and Virgo, which is then in Italy, which was observing, and it was localized to about 30 square degrees of the sky. Now, the thing is, gravitational wave telescope does not give you an image of the gravitational wave. It does not give you a direct, it tells you where the general direction, where the source is. It is like a microphone. If you detect the sound, it doesn't tell you where the sound is coming from. So you require 2 microphones or even 3 microphones to figure out where it is coming from. So because at that time, actually only the 2 LIGOs detected it. Virgo was not operational strictly at that time. So the 2 LIGOs detected it. And then the Virgo data was added to it later on. But at that time, the 2 LIGOs detected it, and they localized it to about 30 square degrees. Now, 30 square degrees is, if you think of how big it is on the sky, you can see here, that is the whole uncertainty region of the source. And if you want to find an electromagnetic counterpart, like a gamma ray source or a radio source or an optical source, how would you find it? The size of the full moon is half a degree. So roughly it is 1/4 square degrees, the size of the moon or the sun. And 30 square degrees is so much bigger than that. And there are millions of galaxies or stars in that region, right? So how would you find it? And actually, if you localize it, then there are so many other physics things that you can know. Now, we were very lucky that at that time, optical telescopes actually told us that there was a burst that had happened at the same time. And you will see it soon. So 17th of August 2017, LIGO Virgo detects the binary neutron star merger. Within 1.7 seconds of this detection, Fermi Integral, which is a gamma ray telescope in space, found a gamma ray burst, a burst of gamma rays, which they had also some kind of an idea of where it was coming from. It was much better than the uncertainty in position was much better than the 30 square degrees that you saw. So Fermi followed up saying, aha, in the same general direction, there is a gamma ray source. And then other telescopes, both in space and on the ground, were turned towards this source. And X-ray telescopes and optical telescopes, etc., they started detecting it about 11 hours after the detection in gravitational waves. We also learn now that how when, say, 2 neutron stars will merge, how long it will take for them to actually generate enough waves in the other bands, in the electromagnetic bands, so that they become detectable by other sources. So even now, multi-wavelength follow-up is going on. So you can see that this lag of 1.7 seconds is seen here. The gravitational wave detection is shown in the bottom panel, and you can see 1.7 seconds later, suddenly in the gamma ray train that you get from the Fermi telescope, you saw a spike that shows it. And the localized, so what happened was 10 hours after the this event happened, people were looking in the general direction to see whether there were telescopes, optical telescopes, that could find something that showed an optical burst in normal light. And you can see that this is what was found. It was found August 17th, that in this galaxy, NGC 4993, which is a nearby galaxy about 40 megaparsecs away, an optical transient was found, which is like this. And it was very similar to in the direction of the gamma ray burst as well as the gravitational wave burst. And then all telescopes started looking at it. So as you can see here, that a large in NGC 4993, this is what it looked like in the optical, but you can now see that in so many different wavelengths, it showed up in the gravitational. In gamma rays, there were many telescopes that that monitored it. In X-rays, Chandra and Integral and Swift, they all found after a little while, after a few hours, they started observing in X-rays. Unfortunately, our own Indian telescope, AstroSat, was behind the Earth at that time, when X-rays were being detected. And then ultraviolet in Swift and Hubble Space Telescope, it became seen. The optical telescopes start picking it up, and then infrared telescopes started picking it up. That this was 2017, it was before JWST, but HST had and various other telescopes in space and on the ground like Vista have infrared observers observing instruments. And then radio. GMRT from India is one of the major telescopes that actually observed it, and so you can see multi-messenger astronomy was born to some extent on that day, because this is the first time gravitational wave sources were followed up by electromagnetic telescopes. And so you can look at all of these different things. They all started falling together, the VLA and Chandra, X-ray, radio, and different parts of infrared and optical astronomy. All of them gave a picture of what this actual event was, and it was actually the merger of two neutron stars causing what is known as a kilonova. A kilonova is 1,000 times as bright as a nova. It is not a supernova, but a nova, as the brightness from the brightness. It comes, a kilonova is about lasts maybe 1 to 2 days. A supernova lasts 30 days. And it emits in optical, infrared, ultraviolet, but we started to learn what else it can emit in different parts of the spectrum. And we can also find different parts of radiation that can come due to the radioactive decay of heavy elements that are found when neutron stars merge. This not only taught us a lot about how multi-messenger astronomy can happen, but it gave us a lot of insight into the physics of neutron stars and what happens when neutron stars merge. One of the key things about such events is that the genesis of elements on the Earth is very interesting. You know that the universe at the beginning has given us a lot of energy, but it also gave us hydrogen and helium. And some of the lighter elements that you see in the periodic table, lithium, boron, carbon, oxygen, even the ingredients of the proteins that make us, are made in the centers of stars in fusion. the fusion reactions that make the light that make stars shine. However, if you go up the periodic table, and here, if you look at the boxes that are marked yellow, they are mostly made in high energy phenomena, like, for example, merging neutron stars. So almost all the gold and platinum that we have, amongst the things that we wear, I'm wearing a platinum ring right now. I'm sure a lot of you who are listening to this are wearing gold jewelry. Almost all of it is actually made in some two neutron stars that have merged somewhere in the galaxy. And then they get to that, these elements get together, and they were there in the nebula that formed the Earth and the Sun, and they got trapped under the Earth, and somebody dug it up and made them into rings that you're wearing. So if you want to know about the origin of the elements in the universe, you have to study things like this. And the 170817, the gravitational wave, showed us two neutron stars merging in action, and gave us so much information across gravitational waves and electromagnetic waves that we've started learning about the production of these elements in these objects only from observations like this. And I hope that this will actually make us understand a lot of basic things, like the origin of the elements of which we are made. A kilonova, which results from two neutron stars merging, produce 16,000 times the mass of the Earth in heavy elements in one event. And it just, the gold and platinum, about 10 Earth masses worth of gold and platinum comes from one of these events. I mean, if you could trap all of that and sell in the market, you'll be very, very rich, of course. There are so many things about neutron stars that we don't understand. And this is why, and I borrowed this from people in the LIGO collaboration who have been planning a lot of these follow-ups of the gamma ray bursts to figure out about what we want to learn. We don't know where these gamma ray bursts, which also are seen in all over we know about almost many hundreds of gamma ray bursts. We don't know what causes them. We know that they are caused by neutron stars or magnetars, but we really don't understand them. We don't understand kilonovae. So apart from learning basic astronomy, we want to learn about how these objects actually are formed. And then we are asking also the question, we're talking of all the heavy elements. Are they all produced in such mergers, or there are many ways of these things that can merge? You know, the LIGO-Virgo-Kagra collaboration of gravitational waves has now given us, in the first 3 runs up to 2020, it gave us about 100 objects. Now it is up to, in 04, is up to almost 250 to 300 detections of neutron stars merging and black holes merging. And if you look at these, you can see that the blue things are all black holes that have been found. Each event that are found is actually involves 3 black holes. There are 2 black holes that merge to form a 3rd black hole. And so all 3 are measured there, here, and they are seen as in solar masses, the mass, that is the y-axis. And you can see the heaviest black hole that we've been found is about 185 times the mass of the sun. This is the first time we are seeing such absolutely massive objects. And you can see there are at least 7 of these are above 100 times the mass of the sun. We had never seen such things before. But if you look down there, you will see that there are neutron stars. The ones that are marked in orange are the neutron stars that are found in through gravitational waves. These merged. Some of them merged into black holes. Some of them are neutron stars merged with a black hole to form a black hole. And there are 2 neutron stars that merge to form a black hole. And so those are marked here as well. And all of these could have been followed up in a multi-messenger follow-up, but only one has so far given us this kind of amazing information, the one I showed you. And so we are hoping that once we get this whole idea of how to follow up gravitational wave events with telescopes that even measure various kinds of electromagnetic waves, we will be able to learn so much. The only one source has given us so much information that we can learn how to follow them up. The gravitational wave spectrum goes all over. There are many, many types of gravitational wave sources. There can be supernova remnants. There should be gravitational waves from the Big Bang. There are gravitational waves that can come from the merger of supermassive black holes, which are in the middles of galaxies. All of these can at some point be detected when future detectors can be detected by multi-messenger astronomy. I'll briefly talk about the various other kinds of things that we need to be followed up. We know cosmic rays we have been detecting for a long time. For more than 100 years, Indians have been very great in actually detecting cosmic rays. These are high energy particles that come from celestial bodies. They can come from quasars. They can come from high energy phenomena that take place around neutron stars and black holes. In India, we've had a very long tradition of cosmic ray detection. They had detected from balloons that, of course, are launched routinely by the Tata Institute from Hyderabad, for example, or they are detected by spaceborne observatories such as AstroSat or various other ISRO-launched vehicles, and of course many other observatories all over the world. They are the most energetic form of electromagnetic radiation, and particulate radiation is gamma rays. Particles are cosmic rays, but gamma rays are the most energetic form of electromagnetic radiation. And we talked about that. And gamma rays can be detected, of course, by gamma ray detectors that are above the atmosphere, because gamma rays don't come through the Earth's atmosphere, and they are produced in very, very high energy interactions that are that take place in high energy environments, such as around black holes and neutron stars, or in blazars, or in active galactic nuclei, and they can be detected by by our specialist detectors, which are in space. Gamma rays also act as messengers. So just like gravitational waves come to us, gamma rays, which are not quite related to the other electromagnetic forms of radiation, which are thermal radiation. These are very specialized physical processes that can come to us. Now, here you can see it's a version of a plot that I'd shown in my previous slide, and that is to show that the atmosphere lets in only a certain part of the optical light and radio waves, but it does not let in most of these different kinds of radiation that will act as messengers. And you can see that for gamma rays and ultra high energy gamma rays, as well as X-rays, we really need to be in space. And this is why we are talking about it in this particular series of lectures, which talks about the space observations. Another most important thing that I want to talk in the last phase of this talk are high energy neutrinos. Neutrinos are produced in profuse amounts by nuclear reactions that accompany a lot of these sources of electromagnetic radiation. For example, think about our sun. Our sun is producing the sunlight, which we see as light, as optical radiation, from a fusion process. Now, in this fusion process, which is a nuclear reaction, neutrinos are also produced. And there's a huge number of neutrinos that are produced by the sun, solar neutrinos, and they just pass right through us, through the Earth. In fact, right now, all of us are having neutrinos passing through our bodies, millions and millions of them. Now, we need detectors to detect these things, but as you know, neutrinos do not actually interact with conventional matter. but they have a lot of information about the original source in which that nuclear reaction was taking place. They are not deflected by the fields, the galactic fields of magnetic fields that are in between the stars or in between the galaxies. So they come right through, which is great because they're not absorbed by anything in the universe, and they come from very, very long distances, and they can escape even from the centers of astrophysical objects, like the sun, for example. You can see neutrinos from the middle of the sun that reach us. Very difficult to detect because they do not interact very easily with matter. So one of the most important detectors that of neutrinos that we have now is in the South Pole, in the Antarctic South Pole. It's built by the University of Wisconsin, but it's a global collaboration called IceCube, and it involves about it's a cubic kilometer of ice in the South Pole, and it has got a lot of sensors. You can see a cubic kilometer. It's got all these sensors embedded in this cube, and the idea is that neutrinos are going through anywhere, of course, going through us, but underground. The IceCube observatory is this 1 cubic kilometer of ice that is now lined with detectors that will detect Cherenkov radiation that is given by neutrinos passing through very close to the speed of light through ice. Now, you can see the size of this whole thing. That is the size of the Eiffel Tower, which is 300 meters tall. Now, this whole thing, as you can see, is very, very tall, and it's embedded inside underneath. And it is underground because what happens on the surface is that there are a lot of other particles that also are coming through, the cosmic rays. And these cosmic ray showers, these cosmic rays come through from distant sources, but they also come to the top of our atmosphere and cause cosmic ray showers. And those high energy particles do not have much information from the cosmological sources, the sources that are in the universe, astronomical sources, because they are mostly produced in our upper atmosphere. So we don't want to detect them. There is no information in there. So we want to shield our instrument from them. And so these things normally are under the ocean. And in this particular case, it is deep underground in the South Pole of Antarctica. And you're looking at neutrinos that actually have passed through the Earth or from the other side, and it is being detected there. Now, what it does is that it detects neutrinos that are traveling almost close to the speed of light. But actually, what they are doing is they are traveling faster than the speed of light in ice. The speed of light in water or ice is lower than the speed of light in vacuum, right? And so if something is traveling very fast, it can actually exceed the speed of light. But because that's not disallowed. What is disallowed is that you cannot travel faster than the speed of light in vacuum. But it is going at the more speed than the speed of light in ice. And so as a result, it creates these conical structures of radiation, which is called Cherenkov radiation. And that can be detected. It's a very telltale signature. And if, for example, the whole place is lined with lots and lots of detectors, optical sensors that are, as you can see, the IceCube array has 5,000 optical sensors. It gives you the direction in which Cherenkov radiation is coming up, and you can detect them. Here, too, there was a fantastic event in 2017, the same year that produced the 1708-17 gravitational wave. And this is called IceCube 1709-22A. It was in September, a month after the famous gravitational wave event, in which IceCube detected almost 300 TeV neutrino event on the 22nd of September in 2017. And this, within 43 seconds, an alert was sent to telescopes worldwide. And of course, the telescopes are, and I'll talk about it a little bit in a minute, are on high alert that if an alert comes from any of these observatories like LIGO or IceCube, they will stop what they're doing and they'll switch, because these things don't last very long, and to switch to the general direction of the source and to find out where it is and to see whether they can observe it. And in this particular case, it was telescopes worldwide. Fermilat already observed a gamma ray flare in that direction, just like they had detected the gamma ray from the 1708-17 gravitational wave. And it was pinpointed as a source. It was called TXS 0506 plus 056, and it was identified to be a blazar. A blazar is a kind of a active galactic nucleus, where what you're doing is that it is an event that is happening around a black hole. It is an accretion disk that around a black hole, but the way a blazar works is that the radiation that is coming from around the black hole is beamed towards us. And so we are looking down the beam, and that's a blazar. And as mass falls in to the black hole, it gets very close to the black hole, and it can actually give you a lot of energy that comes out. And in that kind of bursts, you can have nuclear reactions that can create neutrinos. So right now we have these space telescopes that can do multi-messenger follow-up. These are large telescopes. You know the James Webb Space Telescope is working. SWIFT is on its way out. Fermi's Space Telescope has been doing some amazing work. The Gamma Ray Burst Monitor, for example, and I gave you two examples of where Fermi LAT and Fermi GBM have followed up in 2017 the two archetypal instruments, events that happened in gamma ray in gravitational waves as well as for neutrinos, and they managed to detect them. There will be, of course, in the future, LISA that will come, which will be a gravitational wave detector in space. I will end by saying that there is a wonderful setup that has been proposed for ISRO called Daksha, and I borrowed these slides from Varun Bhalerao, who's the PI in IIT Bombay of the Daksha project that ISRO is now considering to build, which will be a multi-messenger follow-up of such observations. As I said, right now SWIFT is on its way out. AstroSat is declining in its capability to observe. It has been there for more than 11 years now, and most of its instruments are now phasing out. So soon we will not have AstroSat observing, but in sky we have Fermi and Integral. This slide is taken from Varun Bhalerao's talk in the last Astronomical Society of India, and he essentially showed that there are many others which are now coming up all over the world. And what Daksha will do when ISRO builds it, and there are many institutions in India who are collaborating to build it, led by IIT Mumbai, but also institutions like IUCAA and TIFR and PRL are associated with it. It builds on instruments that have been built by Indian institutions for ISRO. And for example, for Chandrayaan XSM, there was a low energy detector that was built for detecting objects that are lower energy in the X-ray gamma ray range. We have CZTI detectors that were built for AstroSat. That you can see that it detects photons in 20 to 200 keV, and the highest energy ones, the sodium iodide scintillators, which go up to 1 MeV. And so here is Daksha is going to orbit the Earth. There were two satellites. There will be two satellites going around the Earth for continuous all-sky coverage, so that when one is one side of the Earth, the other is looking at the other part of the sky, and which will be able to swing within seconds of some gravitational wave or neutrino being detected. The whole point, the challenge is to set up a global alert network all through the world, including space and on Earth. And so you can see that once gravitational wave or neutrino detectors will produce a signal, LVK or as cube, there will be some kind of a processing that will happen in seconds. And this whole thing is being set up so that they will actually process the signal and to find out whether it's genuine or not. And a global notice will be sent out as a virtual observatory event. This whole global alert network is now being set up, and the observatories like Swift, Fermi, JWST, Daksha will then respond, and within seconds, because many of these events can actually maybe the gamma ray part will last only for a few seconds, and then slowly after many hours the X-rays will start emerging and the optical light will start emerging. They have a slightly longer term, and the radio, they have a slightly longer time to respond to it, but the higher energy things happen very fast. I'll end here by saying there are two very nice books that are written on multi-messenger astronomy and astrophysics. If you're interested, you can try and look for them on the web or in bookshops, and you can study these things. I'll stop here and see if people have any questions. Thank you.
Yeah. Actually, we will see whether some questions are there.
Yes.
I request the participants to put some questions in this chat box. Yeah.
Yes.
So one interesting question is, can gravitational waves provide information about regions of space that are otherwise invisible to electromagnetic observations?
Very, very good question. And that's absolutely right. Because, you know, there are many situations from which electromagnetic waves cannot emerge, right? For example, black holes. Now, if you look at black holes, from black holes, nothing can come out. But in the regions around black holes, also, you will find that electromagnetic waves, it is difficult for electromagnetic waves to be produced. But because it's a gravitational phenomenon, very strong gravity can produce gravitational waves. There is no source of electromagnetic waves there. And because you need charged particles to produce electromagnetic waves. So but then anything that gravitates has gravitation. So it produces gravitational waves. Another good example is the Big Bang itself. When the Big Bang happened, soon after the Big Bang, space and time were created. There was a lot of energy. Now that must have produced a lot of gravitational waves because already gravitation was there. There was no charged particles then, no electromagnetic fields there. And so you cannot have electromagnetic waves from the Big Bang. In any case, the universe was so small, it was opaque. And so electromagnetic waves that were produced in the first maybe 300,000 years of the universe, they were being absorbed by the radiation and matter that was there. And so the universe was not transparent. So electromagnetic waves from the early part of the universe don't reach us. But we believe that when LISA will be built, we will be able to detect gravitational waves that are from the very early part of the universe. There are many such astronomical situations where gravitational waves can be generated, but there is no source of electromagnetic waves there.
Thank you. Since gravitational waves carry information about space-time curvature, what future advancements can help us extract more detailed physics from them?
Yes, so I mean, I did have a slide which I rushed through very much, and that is to do with how much you can learn about the nature of space-time itself and general relativity. For example, I'll give you an example. See, black holes are merging to produce gravitational waves, right? Now, these black holes also have spin. Black holes have mass black holes have energy, of course, but black holes also have spin. Now, the spin of a black hole is a mystery because we've never detected them. Theory tells us the spin of a black hole. It can cause very interesting effects in space-time. As the black holes spin, the space-time itself gets dragged by the spin of the black hole. Now, as the two black holes merge, the angular momentum of the black holes also add up, and the spin of the final black hole is related to the spins of the original black hole. These cannot be related to any electromagnetic phenomena that will show up in electromagnetic waves. But the gravitational wave can tell us about the spins of the black holes. In fact, already there are very nice measurements of spins of black holes. This is just an example. There are various gravitational phenomena that comes out of general theory of relativity that can be tested. And general theory of relativity itself can be tested by gravitational wave detections to see whether that is actually the most accurate theory of gravitation, or there is something that is more advanced than GR. All this is going on right now because this kind of astronomy is only 10 years old. Now, with multi-messenger information, with more electromagnetic information about the sources, as well as neutrino information about the sources, this gives more and more information about each of these objects. So putting together is a wonderful challenge, and it's opened up a very, very interesting vista in this whole subject now. And as I told you, we have only one example in neutrinos and gravitational waves where such follow-up has been done in great detail. Imagine with all these facilities coming up that I talked about in the next few decades, what will happen. And this is where young people who are coming into the subject now will get the chance of working on these things. I mean, I kind of envy you, the fact that all this new data is going to be available now for you to work on.
Maybe related to that only, what are the expected contributions of LIGO India to the global multi-messenger astronomy network?
Yes. So, I mean, I told you that a gravitational wave detector is like a microphone. It cannot tell you where the thing is coming from, pinpoint the source. But if you have 3 microphones in the room, and if they're very far away from each other, from the relative time and also the brightness of the sound, the level of the sound, you can figure out where the sound is coming from, right? So similarly, if you have 2 gravitational wave detectors, like there are 2 LIGOs in the US, they can pinpoint the source, but you can say over a large fraction of the sky, the source is there. So multi-messenger follow-up is very difficult, as I showed. We just got lucky for the 2 neutron stars that were merging that we found a gamma ray burst. But with LIGO India, which is at the other side of the world, there will be 3 with a huge baseline between them. So simulations have shown that when LIGO India will operate, along with the 2 in the US and maybe even the 1 in Europe, together, if they all detect the same source at the same time, there will be a lag between them. Then they can pinpoint the position of the source of the gravitational wave to maybe within 1 square degree or half a square degree. And there, with all these different kinds of telescopes, they can very quickly search that half a square degree and find how many sources there are and pinpoint. And once you pinpoint the source in electromagnetic waves, you learn so much about them, right? About the actual source. So multi-messenger astronomy depends on how well we can pinpoint a source in the sky. And LIGO India is going to be invaluable because it's on the other side of the Earth. This is why I think originally the LIGO people wanted it to be in Australia, but Australia said, no, we don't have the money. And very luckily, our government agreed to host the 3rd LIGO. It is going to be built in Maharashtra. So it will be wonderful. And also, because it is now being built slightly later than the original LIGOs were built 20 years ago. the technology that LIGO India will have is much more advanced. The computers are so much more advanced. The lasers are more advanced. The mirrors that are being built there are far more advanced than the original LIGOs. So LIGO India is going to be more sensitive than the original LIGOs that are in the US. So I think we'll get a wonderful world-class performance from LIGO India.
Okay, maybe one last question. Yeah. What key physics insights were derived from GW170817?
The GW 170817, which is the binary neutron stars, has given us a huge amount of physics. And in particular, you know, what happens is that we don't know what is inside a neutron star. Neutron stars are made up of neutrons. But neutrons, when you have 10 kilometers, a star that is 10 kilometers in radius, and is entirely made up of neutrons, you need to know what is the equation of state of a neutron fluid or neutron solid that makes up the neutron star. Inside, it's only neutrons. So the nuclear physics of a star made of neutrons is a mystery. And so when two neutron stars merge, they oscillate. And that gives us a lot of information in that whole signal that you saw of the nature of the solid or liquid that is in there, fluid, right? So we can know the equation of state, for example, which is the thing that relates pressure and volume and temperature of a plasma or a fluid. We don't even know that for a neutron fluid, what it is like. So people who work on neutron star matter, people who work on this degenerate matter at such high densities. Imagine a whole star, which is about 1.4 times the mass of the sun, is in a volume that is the size of a city, right? 10 kilometers. What is the physics of that kind of matter? In order for us to understand where these elements are coming, I'm saying all gold and platinum that I own comes from neutron stars merging, right? So if somebody asks you, how does that produce gold? You have to figure out the physics. Now, that physics we are learning from actually seeing neutron stars merge. And that was the only time we've seen it merge that has produced so much data in other bands is 170817. And I'm hoping we will have 10, 20, 50 such events with multi-messenger astronomy, and then we'll start learning about what neutron stars are like, what happens when they merge, what are the physical changes that happen, what is the chemistry of it, and things like that. It's a new subject completely. Thank you very much for your questions. This is very nice.
Thank you, Professor Somak, for a very informative and interesting lecture. No, this is giving more insights to our participants, especially gold, platinum, all these things, where it is coming from, the source. So let us expect more research in this direction from this next generation participants.
Thank you very much. It was a pleasure working with you. Wonderful. See you then. Bye.
Thank you so much. Bye.